Hello and welcome guys to differentiating logarithms. So just firstly, this lesson, we're just going to learn just how to do the basics of differentiating a logarithm, and we'll look at a couple different examples and scenarios where you need to differentiate logarithms. All right, so let's move on to, so this would be, I guess, the notes for this lesson. The heading is differentiating logarithms. And these are our notes. The derivative of a logarithm becomes a fraction where the log disappears. Just like when differentiating exponentials with logarithms, we only need to differentiate the natural logarithm. So that's log to the base e. So I'm referring to things like that. And just remember, if you're not familiar with the notation, because log to the base e is so common, it's actually more common than using log to the base 10 in our course. There's an abbreviation or a shortcut for that, which is ln, which stands for the natural logarithm, because this is the logarithm that you see so often in the natural world when you're using mathematics to model real-life scenarios. Anyway, so the way we differentiate the logarithm, so if you've got ln of f of x, when differentiating, it'll just become f dash x all over f of x, where that is f dash x is the derivative of the function all over just the function as it was. So it looks like it might be a little bit confusing here until you start seeing some examples. So let's get straight into that now. Example 1, we're going to differentiate the following. So I've got a couple different scenarios here where we're going to differentiate. Let me just change the color. Okay, so let's say we want to differentiate this logarithm here. We've made the domain just all the values of x that are greater than -2. The reason for that is because, remember, log functions don't exist for negative values, or in fact 0 as well. So if you think back to what the log graph looks like, that's it there, and it heads on off to -infinity as you get closer and closer to 0. But a log graph does not actually exist at the point 0 or for any of these negative values. So that's why, we're restricting the domain there. All right, so how do we differentiate? So if we differentiate y, whether you call it dy dx or just y dash, it does not matter. All right, so the log disappears and it just becomes a fraction. Now, on top of the fraction, it'll just be the derivative of the f of x, right? This is our f of x here. So we just differentiate what's inside the brackets there, in which case that just becomes a 2. On the bottom of the fraction will just be f of x, the thing completely unchanged. And that there is the derivative. This one does happen to simplify a little bit, so I will do that. We've got factors of 2 top and bottom, so it actually end up just becoming that. But yeah, that's how you differentiate the first one. All right, let's see this again with another one. This time we want to differentiate the function log of x squared. And again, we don't want the log to be 0 or negative. So we don't need to worry about the negatives because x has been squared. But yeah, x cannot equal 0 in this scenario. Okay, so how do we differentiate? This time I'll use the other more formal notation of differentiating. So y will become dy dx or y dash. And when differentiating a log, the log disappears and it turns into a fraction. The derivative goes on top and the original function unchanged stays on the bottom. And if you can, you simplify. That's the basics of differentiating logarithms. That's how it works. Let's see it again. All right, so now we've got a scenario where we're looking at a rates of change type question that's going to involve a logarithm. So the experience earned by playing a game E relates to the time played T by this equation here. Okay, so we've got this equation here. Now, part A just asks how much experience you've earned after playing for 0 hours. So if you've played a game for 0 hours, you can probably guess. But anyway, let's plug it into the formula and see how real life this formula actually is. Okay, so the experience will be 150 log of 0 plus 1. When you type that into the calculator, you end up getting 0, right? The reason for that is because log 1 is 0. So, okay, it actually looks like it kind of does reflect a real life scenario here. If you've played the game for 0 hours, you've probably acquired 0 experience in that game. Now let's look what would happen if you've been playing the game for 1 hour. So our experience is 150. ln in this case 1 plus 1. So you end up with 150 log 2. I'm leaving it there as an exact value, but if you type that into your calculator, you'll get a decimal, and for like a video game scenario, it would just be rounded to the nearest whole number. Either way, it's not 0. Hey, you've been playing for an hour, you've earned some experience. It'll be about 200 and something XP. All right. Our next question, which is part B of that same one. So we've still got this like formula. There's this game that we're playing. And as we play the game, by the way, I just realized that X should be a T. Just changing variables just randomly throughout. So we've got this formula here. As you play the game, you end up earning more and more XP. At what rate is your XP increasing after 1 hour? So we'll find that. So let's just quickly go ahead and do it. What color am I using for solutions? Orange. Okay. All right, so our formula is this. 150 ln t plus 1. Now, if we want to find the rate, right? That's the rate at which it's changing. Well, we need to differentiate. So let's find the rate at which the experience is changing over time. Because obviously if you're playing the game, the experience isn't like capped out yet, you would assume. It's going to continue to increase. So it is going to be changing. So let's differentiate and get an expression which will give us this change. So we've got 150 stuck out the front. That's fine. I'm just going to ignore that for the moment. Let's differentiate this logarithm. So this is, I guess, the whole thing that we're learning today. To differentiate a logarithm, the logarithm goes and it turns into a fraction. The derivative of the f of x, that's this part here, goes on top, which is just a 1. And that function unchanged goes on the bottom. So in this particular case, this here, and let me just tidy it up a little bit because we've got 150 times 1. Some people do these crazy things where they try and times the 150 to the bottom as well, but just remember 150 is technically 150 over 1. So the top gets timesed by the 150 to become 150 on the top, and you're actually timesing the bottom by a 1, which is why I've just got the t plus 1 there. All right, so we've effectively differentiated. And now going back to the question, we want to find at what rate this experience is increasing after 1 hour. So after 1 hour, we're going to let t equal 1. So our rate at which the experience is changing will just be 150 all over 1 plus 1. In other words, you end up with 75. This would be experience per hour. So that's technically the rate at that particular moment. At that moment, your experience will be continuing to increase at 75 per hour. So that's the end of our second example. Okay, so the third example is just a completely random bonus example, which is an exponential. Just because you see exponentials done so closely related to the logarithms, they are inverse functions. I thought I'd just throw in this bonus question. The temperature T of a cooling pie is given by this. So the temperature is going to be 20 plus 60 e to the minus 1t, where T is the temperature in degrees Celsius and little t is the time in minutes. Okay, so the idea is this. What we're going to do is just find a couple different things related to this. In this particular case, what would be the initial temperature of the pie? Right, for this you would let little t equals 0. And you'd end up with 20 plus 60 e to the ultimately minus 0.1 times 0. Okay, so in this case, you end up with 20 plus 60 e to the 0 ends up being 80 degrees Celsius. This pie was initially 80 degrees Celsius. If you wanted to find the temperature at any particular time afterwards, let's say after like 1 minute, you just type 1 into that formula, re-go through, replace that t, the little t up there in the formula, referring to this guy with a 1, type it in, and you get the temperature after 1 minute or 10 minutes. And by doing this, you can work out, if you like your pies at 50 degrees Celsius, how long would you need to wait until it's 50 degrees Celsius? And again, you're then just solving an exponential equation, and a pretty easy one at that, to be honest. So pretty fun sorts of questions. I guess because we've been covering differentiation and rates, it would make sense to have a question related to that. Let's say, at what rate is the temp dropping? I'm assuming it's going to be a negative gradient here. At what rate is the temp dropping after, let's say, 10 minutes? Okay, so in this particular case, you'd go through, if you want to find the rate of something, you got to differentiate. So this is the original formula. Differentiating, I'll just use the shorthand notation, t dash. Okay, 20 would disappear. Differentiating the exponential, remember the derivative of what's at the top comes down the front. So you end up with 60 times a negative 0.1. And then this part remains unchanged up the top. Okay, so I've differentiated it, and we're gonna let t equal 10 for the 10 minutes past. So the rate at which this pie is cooling after 10 minutes would be minus 6 e to the negative, in this case, 1. And so, I'm going to leave it exact. That's the exact answer. But, you'd probably type it in the calculator and, round it to the nearest number. It depends on how accurate you want to be, really. By keeping it exact, I have it exactly accurate. If you wanted to rewrite it a little bit neater, if you really hate your negative indices, remember you can always bring that e down the bottom, minus 6 all over e. Notice how it's going to be a negative value, right? Which is kind of cool because the pie is cooling. So you want the rate to be negative. That means it's going down. I'm actually going to put in one last super bonus question. Let's say, and this is back to the logs. I actually meant to write this in, but I forgot. Let's say you wanted to differentiate this. Now this is x ln x. Yeah, I guess you could always bring the x up the top using log law number 3, but that gets way harder. In this case, you're far better off using, your product rule. When two separate functions being multiplied together, you can differentiate them as long as you know how to differentiate each part individually, which is what I'm doing right now. Differentiating this log, it becomes 1 over x. And so then to differentiate our y, it'll be, remember the formula, u dash v plus v dash u. Simplifying this the best you can. You end up with ln x plus, in this case, a 1. Notice that 1 is not a part of the log. It's outside it. I'm actually going to rewrite them around the other way just so there's no confusion. But yeah, anyway, I'm going to leave it there. Best of luck with everything. If you're wondering about trying to differentiate a log that isn't of base e, like if you were trying to, differentiate this, what I'll definitely recommend you do is you do not need to, we don't differentiate logs of any base other than log to the base e. So I guess if you really were in a situation where you had to differentiate this, what I would recommend is you use change of base. Okay, and then from this point here, actually you're kind of good. Log to the base e is just... Sorry, I understand there's like a super bonus extra question, but it's more just curiosity. And then now you've got, that's just a number that's out the front. Log to the base e, I'm just going to rewrite as ln. And now you actually could differentiate, right? Keep 1 over log to the base. Oh, I should use ln for that too. And differentiating this, becomes a fraction, 1 all over x, and simplify it. So yes, you can differentiate any sort of a log. You would just have to do change of base rule first to get it into log to the base e, and then you can go in. Anyway, hopefully this all made sense. If you have any questions, just let me know. Either leave a comment here on YouTube or email me directly, and I'll help the best I can. All right, best of luck, and I'll see you next time.